All right, so what are some things we can do with this wonderful formula? One is that we can look at sort of the general idea that I can say the sum from n equals 1 to infinity of, so let's say I have the a sub 1 is just 1, and so I'm just going to look at x to the nth power. Now, if I had n minus 1 or n, the divergence or convergence is not going to depend on what that n, whether it was n minus 1 or n. So what we have here really is that this converges, and that x is really playing the role of the r here. All right, this converges for absolute value of x less than 1 and diverges for absolute value of x greater than or equal to 1. So all we're doing is sort of renaming things. Instead of a1 and r n minus 1, I just have x, and instead of n minus 1, I have n, and I'm also not giving a formula for what the convergence is. I'm just saying sometimes it converges, sometimes it diverges. All right, and then what I observe is that whether this series converges or diverges depends on the value of x. So what we call this is a radius of convergence. This has a radius of convergence. This series has a radius of convergence. X is an element of -1 to 1. So if you think in terms of a number line, we're going to see this happen again and again. Here's 0, here's 1, and here's -1. All right. So all the values of x in here cause the series to converge, and everything outside of that radius causes the series to diverge. Right? So the way the series behaves depends on x, and it depends on it in a way that, we call it a radius, because I was writing divergence, which I didn't have to. Like if you think of a circle of radius 1, all right, all the x values in the circle converge. So that's why it's called a radius, but it's like a one-dimensional circle. All right. Radius of convergence. Keep your eye on that term because it's going to come up again later. All right, so what? That's not a big deal yet. Let's look at some other sort of interesting things. Everybody knows that 1/3 equals 0.3 repeating, right? You all know that. But what does it mean? What is 0.3 repeating? It means 0.333, and the 3's go on forever, right? But what does that mean? This really is 0.3 plus 0.03 plus 0.003 plus 0.0003, and it goes on forever. This is a geometric series. So this is geometric with... That's interesting, not what I had in mind, but fine. It's geometric with R1 equals 0.3. Sorry, A sub 1. I was going to do something completely different. Now I'm winging it. Now I'm making mistakes. A sub 1 equals 0.3, and R equals 0.1. Right? So according to this theorem, the sum from n equals 1 to infinity of this sequence, so 0.3 times 0.1 to the n minus 1, that's this sequence, converges because the absolute value of r is less than 1. Right? Absolute value of r is less than 1 there because it's 0.1. All right, so this should equal a sub 1, which is 0.3, over 1 minus r, 1 minus 0.1, which equals 0.3 over 0.9, which equals 3/9, which equals 1/3. Yeah, I'll be darned. I wonder if you could resolve that pesky issue of 0.9 repeating that way. 0.9, which is 0.9. So basically, what we're saying is that all repeating decimals are geometric series. They are infinite geometric series. All repeating decimals are infinite geometric series. So here's this one that people like to argue and fuss over. Okay, well, the r is, so this is a sub 1 equals 0.9, r equals 0.1. Since our absolute value of r is less than 1, this should converge, and we should have sum from n equals 1 to infinity of this infinite expansion, which is 0.9 times 0.1 to the n minus 1 power, should equal my a sub 1, which is 0.9, over 1 minus my r, which is 0.1, 0.9 over 0.9. I'll be darned. It's 1. Yeah, so this is sort of the most mathematically rigorous way to establish the 0.9 repeating equals 1. There are other ways to establish it. For example, 0.3 repeating we know equals 1 from the extended division process. All right, and then if I just multiply both sides of the equation by 3, then I get point. Oh wait, I'm sorry. 0.3 repeating equals 1/3, doesn't it? Yeah, I'm pretty sure it does. And then when I multiply both sides by 3, so then I get 0.9 repeating equals 1. All right, but the problem with this, there are two problems with this argument. One is we don't really know what this 0.3 repeating means. We just keep getting 3s when we do a long division. So we don't have a clear establishment of equality here. This could be just sort of a notational device rather than actual meaningful value. The other question is, does it make sense to multiply a number by an infinitely long decimal? Can we just multiply that in a normal way, or might there be some other multiplication process involved? So this whole derivation is riddled with holes. However, this one is solid as a bean. Yeah, so there's some interesting things. You can also say some things like, what if I had the sum from n equals 1 to infinity of 1.1 to the nth power? All right, well, that diverges. And now I can give a reason, because 1.1 to the n is geometric with absolute value of, let's say r to start with, absolute value of r is equal to absolute value of 1.1 is equal to 1.1 is greater than 1. So absolute value of r is greater than 1. Therefore, this diverges and I don't have to do or think about anything else. Sort of interesting. Well, there's more interesting things, but let's save them for the next video.